plus just so I can keep track of these. Okay, so if up to this point in the course, every time I wanted to have some sort of data, it would be one little tiny piece of data. Like, for example, I might look at final grades, or I might have all, like if I wanted to know every student's name in the classroom and sort them alphabetically or something like that, I'd have a string. Or if I wanted to know how many credit hours everyone had. So up to this point, every time we had a variable, we had individual variables. They weren't really, we could never really put together a cohesive student, if that makes any sense. Like I could have three variables, maybe their name, their their GPA, and the number of credits they had. I could create three different variables, but I wouldn't be able to kind of glue them together and keep them together. Does that make sense? So I couldn't really I could never really have a concept of a student. I could have a concept of a name, a GPA, and the number of credit hours, but I couldn't really have a student. The whole purpose of this thing that we're going to talk about is that a lot of times you want to start to not work at the low-level details. Everything in computing is about abstraction. So in the very, very, very early days of computers, they would actually work with bits directly. And what they would do is they would have these long banks of switches, and then what you'd actually do is put in these switches and then hit a button, and then that would go inside of one of the CPU registers. And then you do a bunch of switches, and then you hit a button, and those switches literally represented bits. And then we got more sophisticated. We got things like keyboards and even those the punch cards. And then we got into assembly languages. So everything is built upon layers and layers and layers. You want to stop working at very low levels. If I'm designing a building and I'm an engineer, I'm typically not concerned with individual grains of sand, right? That would be way, 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 way too low level and granular than I'm concerned about. I'm concerned about big picture details like, you know, whatever structural engineers are concerned about. But they're not concerned with individual grains of sand. At some point, you have to start to build together and say, okay, I'm not concerned with the individual grains of sand. Maybe I'm concerned with a concrete block or a steel rod or maybe a column, like a load-bearing beam or something like that. You know what I mean? So you're not concerned with those low-level details. So we build on top of things, and you start to be more and more concerned with higher-level data structures. And that's what we're going to build here. Is the first thing is we're going to introduce the concept of so it's called the struct, and let's make a student. And it's going to be very simple because you can track all kinds of data with a student, but let's just keep it simple. All we're concerned about is their name, their GPA, and the number of credit hours. Okay, so let's do this. We're going to have type def struct and we'll call it student. So the GPA, let's do this. We'll store their name in a string. So we're going to include string. And then we'll have string name. Now remember I said before, if it's just an arbitrary string, remember we called it S, but in this case it's representing the student's name. Their GPA, and we'll say num credits. And struct is short for structure. It's like a data structure. We're taking this data and we're making kind of a higher level representation. Now I have the concept of a student. I no longer have to deal with three separate variables. I have all these variables are kind of glued together in the concept of a student. Now, to create a new student, I don't create a new name GPA number like we did before. What I do is now, so you know how previously if I wanted to declare an integer, I would do like int I, or a string, I would do string s. Well, we've just declared our own data type. This type def, that's what it does, is it declares a new type. And so now I've declared a new student. So now if I ever want to use a student, I can just type in student because we've declared that data type, and we'll just call them S for right now. And so now I've actually declared a new student. But this gets a little bit tricky because I have these individual properties of the student. How do I get to that? And so we have this special dot notation. So if I want to know the, or set the name of the student, because right now it's just all empty. So let's say, for example, we'll say that the name of the student is John. The GPA is equal to 3.2, and the number of credits is equal to 88. So this may seem silly, like why would we do this? Actually, let me take a step back. So we've got our student, and this is how we would set the variables. Now, anytime we wanted to do something like student name is, this should be fairly straightforward, I think. So we've got this student S, and then anytime we want to have any sort of properties within that, we would just do S dot and then the name of it. Does that make sense to everyone? Now, why would we want to do this? This may seem like kind of a silly thing. So let's do this. Let's write a function, and I want to know if this student can graduate or not. Okay, so I want to basically know if they have at least a 2.0 GPA and 120 credit hours. Let's just say we'll just keep it a very simple function. And so let's do this. So this function is going to return either true or false. And remember, that's our bool data type. It's short for Boolean. And we'll type in can graduate. Now previously, what we'd have to do is type in the individual variable. So don't type this, but if I wanted to know whether a student can graduate or not, I'd have to type in their GPA and the number of credits, right? But because now we have the concept of a student, what we can actually do is just take in a single argument, and it passes in the entire student. Now this may seem kind of silly with just a few of these, but these structs can get very, very large, and a lot of these functions can require maybe 9 or 10 arguments. Rather than having the 9 or 10 arguments, you know, the different things that for a student can graduate, like for example, they might have to, we might check that all their classes or, you know, any fees that they had were all paid up, and that they, all their credits came from an accredited university, you know what I mean, like, or accredited college, those sorts of things. So we might be checking a lot of different things. We're going to keep it very simple, but just keep that in mind. Yeah, we've just been able to change it from 2 properties down to just the one struct, but in practice that can be very, very helpful. And now again, we're working at a higher level. We're working with a student, and we want to know if that student can graduate. And then so we'll do is just some more practice with some just basic conditionals, because it's been a little while. So I want you to fill this in. The student can graduate So fill this in. If they have greater or equal to 120 credit hours and a GPA that is greater or equal to 2.0. Now I realize that's not working code. Translate that into working code. Yeah.
This is out of scope, but it's related to the structure. So if I was doing that same thing, but if I wanted to use like getters and setters, for example, would I want to do that as a class object and not a structure?
So again, if you're using classes.
Would I want to do it as a class, like its own object, if I was going to use getters and setters and?
So there's this kind of debate. So the original C language only had support for structs, and then C. The actual original name for C++ was actually called C with classes. And so it was literally supposed to be just C with classes. And obviously since then it's become a gigantic language. It really depends what you're doing. A lot of programmers will mix the two. And I guess the general rule would be is if it's data only, use a struct. So say, for example, you've got a point. Like say, for example, a GPS coordinate, and all it has is latitude and longitude, and that GPS coordinate can't do anything else. All it can do is it's data only. Yeah. Then you'd use a struct. If it can do something more important, like say, for example, an actual, let me think. Like say, for example, in that GPS class, you could find the distance between two GPS points or something like that. You know, something like that. Then you would use a class. Some people, and I'm guessing because of Java, are class only, and the way the original creator of C++ created classes, there's actually very, very little penalty for using a class over a struct. So I think you could potentially use a class, because then you have the added advantage by using methods. You can have getters and setters, and then you can actually, have some sort of, you can have if statements and checks. Like in that same GPS class, you could check to see that it's an actual valid, like if they try to set a GPS coordinate that's outside of the range of known GPS coordinates, then you could throw an exception. So okay, so let's translate this. So we're going to say s dot num credits is greater or equal to 120, and their GPA, so s.gpa is greater or equal to 2.0, then yes, they can graduate. Otherwise, they can't. Okay, so let's go ahead and test this. I'm just going to comment the cout statement out for now. I don't want to get rid of it, just so you have it for your notes. But let's do this. We're going to say it's going to be Boolean, so we're going to say bool result equals can graduate s, and then we'll say cout graduation status is and by the way, this is very common that there's a relationship between ones and zeros and trues and falses. So 0 generally translates to false, 1 generally translates to true. So in this case, it interpreted that as a 0, meaning that it's false. There is a way within cout statements to translate this into the word true and false, but I think most people are just, after a while, you just get used to this 1 and 0, that you're used to it. And so it's because the student doesn't have enough credits, and so if we gave the student 125 credit hours, we ran it again, we can see that it become 1, which means true. So they can graduate. And again, notice that we're pushing off a lot of this complexity and unreadability. We're pushing this off into structures and functions. That way now I have nice things like can graduate, where we have kind of human readable function names. And if you really do this correct, you can almost read your programs in English. That might be a little bit lofty of a goal, but in practice, it's not quite far off. If you use a lot of functions, you can overdo it, like if you've got a function that just essentially does nothing. Sometimes you can actually make the situation worse, but typically you want to kind of break things up into functions. Okay, but that's a struct. The whole idea of a struct is just to take a bunch of variables and, I don't know a nicer way of saying it, kind of glue them together, treat them as one logical unit. That now we're dealing with a student instead of 3 individual variables. Now notice that in this can graduate, I didn't use name. Now that's very common, is that there's kind of a disconnect. We don't actually have to use every single variable for each function, because another function may care about the name, okay? But we've created a student. We don't really care about the functions that use it. We're essentially saying, okay, here's a student. Do whatever you want with that data. If you want to use one variable, you can. If you want to use no variables, you can. If you want to use all of them, you can. But this is a student. Does that make sense? Okay. Everyone feel pretty solid on this? Because we're going to get into kind of a complicated topic. We're actually not going to have a new assignment today, and there's a reason. Is because I realize I've kind of introduced a lot of new things in one day. Structs. We did a kind of a complicated example for the previous example. And we're going to start to talk about pointers, which are a little bit... Some people conceptually have difficulty with them. Okay, so let me save this off here. I don't think there's really anything else interesting we can really do with this example. Oops. I should get this set up earlier. Okay, so I'm going to draw some things out here. I don't really do this that often. Oh, perfect, okay. So up to this point in the course, every time we've created a variable or dealt with anything related to variables, we've been kind of spoiled that we've been using what are called automatic variables. And the name actually kind of is appropriate because they just kind of automatically appear into existence. We don't really have to care about the computer's memory at all. But all these variables are actually being stored somewhere. They're being stored in the computer's RAM. Eventually they'll make it to the actual registers on the CPU. But they're actually stored in your computer's memory. And we've kind of been we haven't really had to care where or why or how or any of that stuff as far as computer memory goes. Okay, but let's take a step back here, and let me start to explain some things. And this example is going to be kind of tough because it's not like these other examples where we find an average or there's something useful. This is just going to be purely me just walking through a bunch of stuff that might not make sense today. Hopefully by next class it'll make a little bit more sense. And again, this is kind of the part that a lot of people get thrown off by. I think how I want to do this. Okay. So oops, I got it backwards. There are these things called memory diagrams, and your book probably has some, and there's a lot of different ways to draw them. I'm going to draw a simplified memory diagram that's actually it's not actually completely accurate, but I'm sacrificing accuracy for simplicity of understanding. That's probably not enough room. Let's go even more here. That should be good. And let's see here. So I'm going to call this label. We're going to have a memory address and a value. I think I'm going to need more room for the label than anything. So let's do this. Okay. And I'll just scribble for the rest. Okay. So all the areas in your computer's memory, RAM, just for regular PCs, we can sort of think of them as interchangeable. It's a little bit more complicated than that, but we don't really care. This is not like an advanced computer architecture course. So your computer's RAM, every time we create a variable, it's got to go somewhere, okay? And so we have these memory addresses, and they start from 0 and they go to all the way up to a really high number. Now for the program, at any given time, the program that we're dealing with, it's going to be, it's not quite a random number, but it seems like that to us. So let's just pick a number. Let's say it starts at 128. Now this isn't a completely accurate representation, but it's close enough, and it'll suffice for class. And then it keeps on going in the other direction, and same thing. So in both directions, it keeps on going. Now if I declare some variable, let's say int I, so this is some code off to the side, it said int I, what happens is that it says, okay, well, what's the first, I don't like that, let's try that again. Int I, and then a semicolon, there we go. It's going to go to the first memory address, and it's going to say, okay, what's available? So the first memory address that's available is right here, and so it's going to reserve this spot for I. Now, as soon as I give that a value, because right now all I've done is I've declared a variable, and so it says, okay, memory address 128, that's reserved for UI. Now, again, remember, we don't work at low levels. We don't work with individual bits. We get to work with human readable names. That's the nice thing about computers in 2019, is that we don't have to care about these memory addresses. Typically, all we have to do is we do things like add 1 to the address or check if 2 addresses are equal. But in practice, I don't actually have to care about what these addresses are. And actually, if you start hard coding these addresses in your program, it'll be very fragile and it'll probably break more than anything. Now, if I did I is equal to 5, then it says, okay, now we've got a value. We've got 5. And then maybe I do some stuff in my program, and then at some point later on I say, okay, I want I to equal to 7. What we'll do is it'd go back here and say, okay, well now I is actually equal to 7. So we've got this idea of a memory address. And notice that the label is just a human readable label. Computers work with numbers. Computers work with these memory addresses. It doesn't really care what we call this label, because one of the first things it does is it just basically throw unless you've got debugging symbols and all that stuff. But for the most part, it's going to generally throw away these labels, and all it's going to really be concerned about are these memory addresses. Okay. And so if I created another variable, let's say I called it k, same thing is going to happen. It's going to reserve some space for k. And then as soon as I set a value to it, it's going to give it that value. So I want you to understand for right now that there's a very clear distinction between the label that we see in our program, the numeric memory address, and the value. The analogy I've always given, and I don't know if it helps or not, but I've been giving it for a few years, is that you can almost think of it like a mailbox, okay? It doesn't matter what the name on the mailbox is. You know, people can move in and out of the area. What matters is your the address on the mailbox, correct? And then inside that mailbox is the actual mail. And that's kind of distinct from the label or the address, is that it doesn't matter who lives there, what the address is. If somebody walks up and puts a postcard in that mailbox, the contents of the mailbox are going to be that postcard. The contents of that mailbox are going to be 11. So now what we can do is I'm going to introduce these things called pointers. And pointers are interesting. So what you do is to declare a pointer. You do, just like normal, the data type. So I'm going to say it's an integer. And then we use the star. Like you hit the shift key and hit 8. It's going to be the star. And a lot of times we just use the word P or P and then some name like P age or something like that, you know. But P just means that it's a pointer. It's just a kind of the computer doesn't understand it. It's just something we do for readability, if that makes sense. And so what happens is that, okay, now it reserves some space for P. And pointers themselves, you don't typically, the idea of a pointer, and it's in the name, is that you point it somewhere else, okay? So now let me take a quick step back here. At any point in your program, if I wanted to know this value right here, 128, what I could do is I could say, okay, I want, it's the ampersand, so I probably mess up drawing this, something like that. It's basically if you hit the shift key and 7, I could do ampersand I. And that'll give me back this right here, the actual address. It'll give me back 128. So what we typically do with a pointer is a pointer by itself doesn't have a value. Well, it does, but we don't really, I'll explain in a minute. So we've declared a new pointer, and we're just going to put a little, I guess, I don't know how to denote it. I guess we'll just kind of a little star over here so that we know it's special, that it's a pointer. And then now what I'm going to do is I'm going to say P equals the address of I. And what it's going to do is inside of this value, it's going to say, okay, well, what's the address of I? The address of I is 128. So everyone with me so far? So anytime we do ampersand and then the variable name, we're getting the address of that variable. And then remember, we have our distinct things here. We've got our label, our human readable label. We've got our memory addresses, and these are just assigned automatically. We typically don't really ever mess with these manually. And then we've got our values. And then I introduced that, again, that we can grab the address just by putting the ampersand in front. And then now I'm introducing something here called a pointer. And the idea of a pointer is that it points somewhere else. This will make sense later on. It's for efficiency purposes. It's not going to make sense this class. It'll probably make more sense next class, why we tend to use these things. And so what I've done is I've declared a new pointer, and I just kind of marked that over here just so that we know it's a pointer. And then next line of code, I want to say the value of that pointer is going to be the address of I. And then so we go back here and we say, okay, the address of I is 128. So now this is where people get a little bit confused. So I'm going to put a little bit of a line here. So anytime I want to, so let's do this. There's something called dereferencing, okay? And so if I did this, so if I said star P is equal to 4, anytime you use the star P, what it does is it goes to the value of the pointer. It says, you're a pointer. I know that from here, and because you've used that little star, and you're pointing to memory address 128. I'm going to zip over to memory address 128, and I'm actually going to go in here and change that value to 4. Does that make sense to everyone? So what happened is that we said star P, and so it went over here and it said, okay, I know that you're pointing to memory address 128. And again, these are going to be random. You don't particularly care about what they are. Again, like I said, you just normally do it like you want to know if they're equal to something, if that makes sense. And then it actually went in that memory address's value and changed that value right there. Now, if I did, and I'm sort of running out of room, but I think I'm almost done anyway. If I were to do a cout of I, what would it print? I think I heard the right answer. Say it louder. 4, right? Because we've actually gone back here and changed the value to 4. Now this throws a lot of people off because remember at the beginning here we had I is equal to 5 and I is equal to 7. But now without actually ever directly changing I is somehow now 4. And it's because this other variable is pointing to it. So going back to that mailbox analogy, if somebody walked up to a mailbox at some address and put in a postcard and walked away for a little while, and then somebody else just random on the street walked into that mailbox and said, oh, I don't like this postcard, I'm going to put a big frowny face on it, and wrote on that postcard and put it back in the mailbox. Now, if the original person if they walked back over to the mailbox, would they have any expectation that it's going to be the original thing? You know what I mean? Like, unless they've got a lock on that mailbox, there's really no expectation that it's going to be the original thing, right? Because somebody could walk over. And that's the same thing here, is because we've got other things pointing to it, we can do that. Now, this part kind of throws people off a little bit here too, so. What's that going to print? So cout star P. Any ideas? What's that? Exactly. Because remember, anytime we use this star P, it's what we call dereferencing. It's going to go here and it's going to say, go over to memory address 128 and then look at its value. And before we were setting the value, but now we're just reading the value. Okay, is everyone with me so far? I'm going to review that one more time. The reason I'm kind of going through this slow and doing diagrams and stuff is because historically people just, not just at IRSC, just all over the world, this has been one of those things that people have had a lot of difficulty with, so I'm trying to spend some time on it. Yeah?
What makes the I value change from 7 to 4?
It's because of this line of code right here. Because what we did up here is that we said, okay, P, so not star P, but P is going to equal to the address of I. And then that's how we got this line of code right here. We're saying that it's equal to 128, and because we've kind of marked this as special, this thing is called a pointer. We know inside of its symbol table that this is a pointer, this is something special. And then now here, when we do this star P, what it does is it says, oh, okay, go over to memory address 128, and then go over to its value and change it to 4. Now remember, so now if I do a cout, I is at address 128. So again, going back to that mailbox analogy, if I wrote the value, if I wrote 7 on a note card, and then somebody walked over to the mailbox, opened it up, said, I don't like this, crumpled it up, wrote 4 on their own note card and put it in that mailbox. If I walk over to that same mailbox, what's going to be written on it? It's going to be the 4 written on it, right? Because that's the last person to do that. Same thing is happening here. Does that make a little bit more sense?
Yeah, just wanted to understand, like,
Label is so these label is just kind of human readable. The computer actually tends to work with these memory addresses, and so these labels are just meant for us as humans. And there's a direct mapping. So I is at memory address 128, K is at 129, P is at 130, but P is special. P is something called a pointer. Let's do this. I'm gonna minimize this for a second. Let's open up an example. And again, we're not going to do like a very interesting, complete working example. We're going to just do a lot of this. And then next week, it'll make sense, a little bit more sense. I just want to introduce these general concepts. Okay, so let's start up a... Oh. Hold on. 1, 2... No, this should be 3. Did I make a 3?
No, we started 3 then.
Okay, well, that's what we're on. So if you already had a 3 open, that's fine. You don't need to make a new one. Okay, so now let's do that example in code. So we said, okay, we had our int I, and then what did we originally set I to? I is equal to 5, cout I, and then this shouldn't be a surprise to any. Oops, and L. That shouldn't be a surprise to anybody. We've done that a million times. If I changed I to 7, okay, that's so trivial. I'm actually just gonna well, I'll at least get rid of the cout statements. Do you have a question? Or you're just stretching. Okay. Now, if I wanted to know the memory address of I, does anybody remember the syntax for that? What do I put in front of the I? Ampersand I. Oh, that doesn't look like a number. Well, it is. Some of you have taken networking class and other classes. It is a number. What type of number? Hexadecimal, yeah. So for anybody who doesn't know that, you can actually, I think the Windows calculator still let you. Being a programmer. Okay, so I want to put it in as hex. So that might seem weird, but look at this. It turns out that it's just a number, okay? It's a very large number, but it's still just a number. So don't feel overwhelmed by that. It's just an alternative base number representation. It's base 16. Computers work in base 2. If we worked just with 1s and 0s, we would get the numbers to be very, very long very quickly. Notice here that same representation in binary is very long. Hex just makes it so that we have a shortened version. Long story short, you don't really have to care, again, what the number is. Just know that that is a number. Don't think that it's just letters. What happens is that eventually after 0 through 9, we run out of numbers and we have to start using letters. Okay, but that's going to be the address of it. Yeah?
Can you run it again just the way it is? Because then why does the number change? Or at least it was for me.
Yes, so that's interesting. So modern computers are super, super, super complex. And over the years, because of various security reasons and other things, if you had written this program in DOS back in the early 80s, it would be a very low numbered number, and it wouldn't change each time you ran the program. What happened is that there's a type of attack, of a security attack called the buffer overflow. And what would happen is that because of this security flaw, if you knew the specific memory address of the buffer overflow, you could inject code in it and have executable code. And a huge... Does anybody remember how bad Windows operating systems were in the early 2000s? Yeah.
Is that similar to Spectre?
No, Spectre's at the CPU level, but that Spectre's pretty interesting as well. But like in the early 2000s, there was the Code Red Worm, there was SQL Slammer.
I love you.
Yeah, exactly. All these, there was a huge number of these buffer overflow exploits in the early 2000s. And did anybody take CIS 1000 with me in here? No? Okay. This is actually one of the questions I make them go through. What happened is that if you know this memory address ahead of time, it can cause a lot of problems. Not in itself, if this plus a few other things happen, but to try to mitigate that, what they did is they created something called address space layout randomization. And there's all kinds of variations on this technology, but that's exactly what it does now, is every time you run a program, it tries to randomize the address space layout as much as possible.
It tries to, because you can still figure out where it's going to be.
Yeah. And there's just, it's not one technology. It's like it's just like iteration after iteration after iteration for like the last 10 years that they've come up with these different technologies.
Scroll a little bit? Just a little bit? Too much. It's funny, FreeBSD just disables it by default. I mean, it'll show up at 13, but they're like, whatever.
Yeah. Okay, but yeah, so that's why. And again, typically, and remember earlier I said you never want to hard code these numbers in your program. That's why, because they're you should treat them as unpredictable. Now, what you can do is that you can check to see if these two numbers are equal to something. Like you would never hard code this number, but you can just check that if the address of one variable is equal to the address of another. That has context and that has some sort of meaning. But so here we're looking at the address of I. So let's do this. Let's create this thing that we had called a pointer. So we'll do int star p, and then we're going to say that p is equal to the address of I. So now without running this line of code, we've got two cout statements right now. So what are these two cout statements going to print? The same thing, right? Because they're pointing, or so one is going to print the address of I. The other is going to be where it's pointing to, which is the address of I. And we run this, and just like I said, we don't care what the numbers are, but we notice that they're equal. But again, they're going to be different each time. So now let's do this. Let's change the value of I, or no, let's do like we did before. So we said star p is equal to 4. What's line number 22 going to print? So I changed star p, right? Going back to our diagram. Yeah, exactly. So it's going to, star p is going to go over to memory address 128, and it's going to change the value to 4. That way, if we do a cout of I, we get back 4. And then if we also did cout star p, we get that. Okay, so I realize this is very abstract. It's, you know, we're not actually, you know, like, remember the first weeks we would do like these calculators and stuff, and now we're just looking at computer memory addresses. I realize this is a little bit weird, but sometimes I can wave my hands and I can say, don't worry about this for now. But this is one of those topics that I have to actually explain it from the ground up, or else you're just going to get very confused. So does everyone understand the basic memory model so far that we've worked with? So let's take a quick look at something that we've experienced previously. So I'm going to copy this, and then let's do one more example, and then I think that'll be it for today. So this is EX3.
Are you gonna put that drawing that you did too?
I can try. Oops. Does this have everything on the screen? Let's see if we can do a screenshot. So I wrote this drawing program years ago because there weren't any good drawing programs that were just like super basic. And I lost the source code, and I should have probably made a save feature. So this is what this is kind of hokey. This is what I do now. I just make screenshots. Shutter? Okay. The problem I always had with these drawing programs is that they always wanted some big like palette off to the side or something, and I just want literally just a blank white screen.
Either one of those two.
What's the other one you said?
Screenshot or Shutter.
Okay. I made this probably like 5 years ago. I don't even, were those around 5 years ago?
I don't know.
Okay. I hope I didn't waste my time.
That was on Bugshot 5 years ago.
We'll just do a rectangular.
So
That's
if
good
you're on
enough.
Windows, that's another good one too, Bugshot.
Okay, and I'll upload that as well. Yeah. If they didn't save it, it's their fault. It's actually probably mine from another semester. Okay. What were we doing? Oh yeah. Okay. So everyone's good so far. Let's do one final program here. By the way, just to let you know, I don't think there will be pointers on the final exam. I think usually what I do on the final exam is I don't know. I don't want to rule it out just yet. If I do, it'll be very, very simple pointers. Okay, but we'll talk about that later. I don't want to promise something now and then we get to the final exam a few weeks ago, you know, and then, oh, you promised there would be no pointers. If I do, I'll try to keep it simple with pointers. But let's get back to this. Okay, so let's. So let's return to one of our old programs, add two numbers. This should hopefully help some people with something called scoping. A lot of people had difficulty understanding the concept of scoping. And so add two numbers was really simple. We just had int A, int B, and then we can say that int result is going to equal A plus B, and then we're going to return result. We could actually do this in one line of code, but I'm storing this to a variable for a reason. And then what we could do is say that int result is equal to add two numbers, and then just doesn't really matter what we're adding. Let's just, first of all, let's just make sure that it actually works. Okay, so last time I checked, that should be 7. Now, remember we talked about scoping and the whole That was the whole reason I couldn't do something like this. Right, this is not even going to compile. It's because every time I create a variable, that variable is scoped to that function. There's very complex scoping rules, but for this class, we can just think of each variable scoped to each function. And it probably didn't quite make sense at the time because it's like, okay, I've got these two variables result, and you know, you can kind of think, well, okay, I guess I sort of understand it, but let's do this. Remember we talked about the memory addresses? Now remember, computers work with numbers. The computers really don't care about the labels. The labels are just for us as people. The computer really cares about memory addresses. So let's do this. We'll say, we'll just say for checkpoint 1, address of result is, let me give myself a little bit of room here. And we can comment this out. We actually don't really care. We know the function works. And now notice, even though they have the same name, because they're in different functions, they're scoped differently. What do you notice about the memory addresses? They're different, right? And so again, the computer, this is, and that's why a lot of people I think have difficulty at first understanding scoping, is because it's like, well, they both have the same name result, but the computer doesn't care about human readable names. The computer deals with numbers. And as far as the computer is concerned, they're two completely different memory addresses. Any questions about that? Does that make sense now? And that's why we can use that label over again, is because every time we have a variable, it's scoped to that function. It's only valid within that function. And we can reuse that name because it's just going to go to a different memory address. The computer keeps track of all that. It actually creates something called a symbol table, where it maps those symbols to memory addresses. Okay. I think I've confused a lot of people enough today. So that'll be it for today. What we're going to do next week is we're going to start to do more realistic real-world examples, and we're going to start to understand why we need pointers. Because the examples I gave today, I didn't really give a good sense of why the heck we need these things. And we actually do. You could technically write programs without them. They would just be unusably slow. They would be 100 times slower in some cases. I mean, they would just be incredibly slow. So we actually do need pointers. Okay. Any questions about anything that we covered today? Because we're doing okay on time.
Not sure if this relates to what we're working on in here, but if you want to detect blank input when you're asking for CN and have the program just loop back to asking for input again, how would you do that?
So if you hit the enter key, it doesn't say that it doesn't just give you back a blank string.
Nope, it just freezes. It just stops working.
I'll help you individually with that.
Sure.
Since the
I just know that was broad enough to cover just to enter it.
I'm thinking that you could check the string length, but I don't want to try like 10 things in front of the class. And so what I'll do is during the break I'll try 10 different things. Any other questions? Okay, so I'm going to post this. So you know what you have out there right now. You have assignment number 7. For those of you that haven't finished this, just get it done. Please get this done tonight in class. Do not wait until next week. I would say that if you wait till next week, you're behind. Just to let everybody know. The reason I do these 2-week out due dates is for emergencies. I don't want it to become like normal. It's get it done that night, or worst case next week. That final week is just for like, I didn't, a million things can happen, but it's really reserved for emergencies. I don't want you to make that the normal thing, because what happens is if you wait 2 weeks, that means you're 2 weeks behind, because we'll have started arrays 2 weeks ago by the time it's due, and then we're going to be on to way more complicated things next week. So just get this done. I know a lot of you are tired. just stick around and just work on it the best you can, and then get it turned in. Okay.
Meet our quota last week. Was it like a certain amount of people finish it before they leave? I forget. Am I just making that up? Did I dream that?
What's that? Oh, what was the agreement on it?
Like
Your 48-hour extension.
On which one? Oh, number 6.
Yeah.
Yeah. Everyone, we met that.
Oh, okay.
And I'll get that graded soon. I completely forgot about that. No, I did. When I checked it earlier, I was like, why were all these lights? I was like, oh yeah, I gave an extension. Okay, so do about a 10-minute break. Be back at 8 o'clock. If you're done all the way up to number 7, we don't have a new assignment this week, so you can head on out, I guess, a little bit early. But for everyone else, if you have not completed assignment number 7 and turned it in, then take a 10-minute break and then be back here at 8, and then let's work on this. So I know there's probably some questions, but let me go ahead and get this uploaded so that I don't forget. This is going to be X4.